So today, we're going on a bit of a journey. We're going to trace the absolutely wild story of how we understand motion itself. We're starting way back with the simple, solid rules of the ancient world, and we're going to follow that thread all the way to a completely mind-bending paradox, one that just shattered everything we thought we knew and paved the way for a revolution in physics.
I know, it sounds like the beginning of a really weird joke, right? But believe it or not, the answer connects a 2,500-year-old piece of math to the very fabric of space and time. They're all key players in our quest to figure out one of the most basic ideas in the entire universe: motion.
All right, so let's start at the beginning. In a world that felt solid, totally predictable, and, measurable. A world built on these absolute rules, where if you just knew how things started, you could predict the outcome with perfect certainty. It was a comfortable clockwork universe.
And the ultimate symbol of this certainty? Good old Pythagoras. For more than 2,000 years, this beautiful little equation has been the bedrock of geometry. It tells us something simple but profound. The distance between 2 points is absolute. It's fixed, it's true for everyone, everywhere. It's a perfect rule for a static, unchanging world. But what happens when things actually start to move?
Well, the thing is, as soon as we introduce motion, our common sense, the very intuition that serves us so well in a still world, can start to get us into trouble. Turns out even something that seems as simple as calculating an average speed, well, it's not as straightforward as you'd think.
Let's try a quick little brain teaser. Picture this. You're on a bike. The climb up a hill is a real slog. You're grinding it out at 5 kilometers per hour. Now the question is, how fast do you have to fly down that exact same hill to make your average speed for the whole round trip a nice clean 10 kilometers per hour? I bet your brain just jumped to an answer. You went up at 5, you want to average 10, so you've got to come down at 15. The average of 5 and 15 is 10. Makes perfect sense. It's simple, it's intuitive, and it's totally, completely wrong. This is our first big clue that the math of motion plays by some very different rules. So why does our intuition lead us astray? Well, it's because the real formula for average speed isn't just adding 2 speeds and dividing by 2. It's something called the harmonic mean. The key is that it's all about how much time you spend at each speed. And because you spend way more time slogging up the hill at that slow pace, that 5 kilometers per hour has a much bigger impact on your final average.
And here is the real kicker. It's literally mathematically impossible. To average 10 kilometers per hour for the whole trip, you would have already used up the entire time budget for the round trip just on the way up. So to make the math work, your downhill journey would have to take 0 seconds. You'd have to travel at infinite speed. It's impossible, and it's just this brilliant example of how motion can fool our intuition.
Okay, so if simple averages are already this tricky, what about speed itself? This brings us to a huge, revolutionary idea, first really nailed down by Galileo. There's no such thing as absolute motion. It's all relative to whoever's doing the looking.
Just think about walking in the rain. If there's no wind and you're just standing there, the rain falls straight down, right? But the second you start running, what happens? Suddenly, the rain seems to be coming at you from the front, hitting you at an angle. The rain itself didn't change at all. Your motion changed how you perceive its motion.
And here's the same idea, just with a bit more cartoon chaos. To someone just watching from the side, that anvil falls straight down. But for the poor guy in the car, his own forward motion gets combined with the anvil's downward motion. From his point of view, that anvil is flying right at him from the front. It's the same exact event, but 2 totally different experiences of motion.
And that's it. That's the heart of what we call Galilean relativity. Velocities just add up and subtract. The speed you see is just a simple combo of your speed and the object's speed. It's elegant, it makes perfect sense, and it paints a picture of a nice, orderly, clockwork system.
Now look, this idea of relativity wasn't just some clever thought experiment. It actually became the key to proving one of the most world-changing scientific ideas in all of history, that the Earth isn't standing still. It's actually hurtling through space.
For nearly 200 years, the whole idea of a moving Earth was just fiercely debated. Copernicus suggested it, Galileo famously got in a lot of trouble defending it, but nobody had that one piece of solid, undeniable proof. That's where an astronomer named James Bradley comes in, almost a century after Galileo.
Bradley was on the hunt for something called stellar parallax. The idea behind it is actually pretty simple geometry. If the Earth is circling the Sun, then a star that's relatively close to us should seem to shift its position against the backdrop of faraway stars over the course of a year. It's exactly like holding your thumb out and watching it jump back and forth when you close one eye and then the other.
But here's where things got really weird. When Bradley made his incredibly precise measurements, he did see a shift, but it wasn't the one he was looking for. The theory of parallax said the biggest shift should happen when the Earth is at opposite ends of its orbit, like in June and December. What Bradley actually saw was a shift that peaked in March and September. The timing was completely off.
And this is where he has this incredible aha moment. He realized the shift he was seeing had nothing to do with Earth's position, it had everything to do with its velocity. It was the rain analogy all over again. The starlight was the rain, and his telescope was the umbrella. Because the Earth is moving sideways, he had to tilt his telescope just a tiny bit forward to catch the light. This effect, called stellar aberration, became the first direct, physical proof that our planet is in motion.
And not just in motion. By measuring that tiny little angle of tilt, he was actually able to calculate our speed. His discovery helped confirm that our planet is whipping around the sun at a mind-boggling 30 kilometers every single second. That's over 100,000 kilometers an hour.
So by the 18th century, everything seemed to fit together perfectly. We had this beautiful, clockwork universe governed by absolute laws, where all motion was relative and you could figure it all out with simple math. But a crack was just about to appear in this perfect picture.
I mean, just listen to Isaac Newton himself. This quote perfectly captures the worldview. Basically, time and space were the fixed, unchanging stage where all the action happened. They were absolute, the same for every single person in the universe. This was the foundation of all of physics, and nobody questioned it.
So what was the one thing that was about to blow all of this up? Light. In the 1800s, a physicist named James Clerk Maxwell came up with these incredible equations that tied electricity, magnetism, and light all together. He showed they were all part of the same thing, an electromagnetic wave. But hidden inside these new laws of nature was a prediction that just made no sense at all.
And here it is, the paradox at the heart of everything. Maxwell's math predicted that the speed of light in a vacuum is a constant for everyone. Think about that. It doesn't matter if you're flying towards a light beam at merely the speed of light or running away from it. You will always measure its speed to be the exact same number. This one thing, light, completely breaks the simple, beautiful rules of Galilean relativity that worked for absolutely everything else.
And that created this impossible situation. How can the speed of light be absolute if all other motion is relative? Something had to be wrong. Either Maxwell's brand new equations were flawed, or the centuries-old foundation of physics from Newton himself, the idea of absolute time and space, was wrong. It was a crisis that forced a complete rewrite of our understanding of the universe. And it leaves us with this final, massive question. If the old rules are broken, what new rules have to take their place?